Hello, can you hear me?
Yes, now I can, yes.
Okay, sorry, my mic got muted somehow. You're making
Okay.
all kinds of crazy noise over there.
I was trying to text you that I couldn't hear anything.
Sorry, I don't even have my phone. I'm supposed to bring my phone when you're in class, and I forgot it today. All right. Sorry about that. Somewhere there's a way for you to message me here. I gotta remember how to do that. Okay, welcome. Oh, I think it's in the upper left corner, maybe? What's that? Chat. Let's try that.
Oh.
Does anything pop up for you? What happens when I...
Oh, yeah, it does have a group chat.
Okay, so hello, Debbie. Do you see that?
Yes.
Okay. So there's a chat there we can use if I forget my phone again. Sorry, I did that to you last week too.
That's all right.
Okay, so we've been reviewing addition and multiplication, in particular going over some problems with project 7 and 8.
Okay.
All right, so now we're down to the area model. And so I recorded what you missed. You can check that out later.
Okay.
All right, so again, what I end up with here, now this is the crazy thing about the area model though. We start off with lengths and widths like inches or feet, but we end up with square units in the end. And that's a whole new thing for kids to deal with. Okay? If you have a room with vinyl tiles, that's awesome, because then you can talk about square units, right? Square feet, they're all over the floor. But some schools are carpeted, but somewhere in the school there's bound to be tiles somewhere. I don't think I've been in many schools. Can anyone think of a school they've been in that didn't have like vinyl square tiles somewhere?
Yeah, Washington Elementary.
Has none?
No, it's all cement.
I don't think West Park does anymore.
Oh yeah, no.
Oh, the ceiling at least has a grid. Yeah, so anywhere we can find a grid, we can kind of get that idea. Especially if there's squares, like the lights here have square grids, right? So we can talk about that. So anywhere you can find a grid is nice. But we have graph paper, right? We can get the idea. And it's not that hard to pick up. But the thing is here, if this was 1/2 of a foot, oops, that's not a pen. If this is 1/2 of a foot and this is 1/3 of a foot, then the big deal here is this is 1/6 of a square foot. Right, so it's a totally different kind of thing. We just jumped from 1 dimension to 2 dimensions. Big deal. So that's a consequence of using the area model. Most of the time it's not a problem, but we do have to consider it. All right, let's do another one with the area model. And Kelly, do you have your test with you? I want to do a problem like on the test, but I don't want to do the same one. You have one of the, yeah, thanks. Do a problem like number 5. So let's explain to you first. I'll do a slightly different one. So suppose we had 2 1/3 times 2 1/2. So I mentioned before in class that it's usually dangerous to try and do calculations with mixed numbers. We should convert them to improper fractions. When you're modeling, it turns out it doesn't matter. So I'm going to draw it both ways. So I'm going to use the area model. And so that means I need to draw something that's 2 1/3 by 2 1/2, and we have to have holes in there. So I'm going to come down this way for my 2 1/3, and then in there I have to mark off my holes. So I need some kind of ruler, so that can be my ruler. 1, 2, and to be able to draw 2 1/3 accurately, I need to draw 3 holes to make that happen. So there's 1, there's 2, there's 3. And then I have to go over here and say, okay, that's 1/3, that's 1/3. So that guy right there is my 2 1/3. So I got to make my own number line there. That's I'm sorry. All right, so then I go the other way, and I got to mark off 2 1/2. So hopefully I made this wide enough. And I want to try to make my 1s the same width. So that's about 1, 1, 1. So there's 1, 2, 3. And so now I can come over here and say right about there must be 2 1/2. So then my area is this right here. This is my answer. Done. Just kidding. It's not done. Yeah, I gotta say, well, what the hell does that big thing mean? Okay, so what are we modeling here? Fractions, right? What's the fundamental definition of fraction? It's fraction. Equal parts of a whole. Thank you for the equal. Yeah, so I have to draw my holes in here so I can see all the equal parts. So now I gotta go back in and griditize this. So I'm going to take my 1 unit here and draw it all the way across. I'm going to take my 2 and draw it all the way across. I'm going to take my 1 here and draw it all the way down. My 2 here and draw it all the way down. And then hope I can start naming parts. Okay, so let's see. I'm going to start looking for holes. Well, 1 by 1 is a hole, isn't it? So there's 1 hole. 1 by 1, there's another hole, isn't it? Down here is another 1 by 1. Is this looking familiar at all, drawing pictures like this? What does this remind you of? Connect floor. Shit, that's not what I was hoping for. That's okay. We'll keep trying. Remember last quarter when we did multiplication of 2-digit whole numbers? This is the same thing. Exact same thing, but now we have fractions instead of pieces of 10. It's the same idea. Okay, so for sure the answer is more than 4. Okay, let's see, what else can I do here? Does anybody know what this piece is right here? No, it's not a quarter. Not a sixth. Well, what's the measurement across here? What's the measurement down this way? So what part of a hole is it? Ah, there we go. It's a half of a hole. Okay. So that's a half there. What about this guy right there? That's another half. So altogether, there's another hole. Okay, so I'm adding up holes here. There's 10. There's 1. There's 2. There's 3. There's 4. This guy right here is number 5. Oh, then I got all this stuff on the bottom. All right, let's see. What's this guy down here? What do you think?
A third?
He's a third, yeah, because he's 1/3 tall and 1 wide. So that's a third. Okay, that's good to know. There's a third. How about this guy right here? Another third. What about this guy right here? Yeah, it's 1/3 by 1/2. We figured out before that's 1/6. Okay, so I have lots of different pieces and parts. Do I have different denominators going on here? Aren't we really trying to combine stuff? Combine's addition, right? Can't we only combine stuff if it's like the same? Okay, so what can I do to make this stuff the same? Halves and thirds. Start splitting them, yeah. I have a half marked right here. I should keep cutting the holes in half. Let's see, if I do that, does it help? Oh, check that out. What do I have across the bottom now that I cut all those in half? Well, not a hole, but each of these pieces has something in common. What is it? How tall is each of those pieces? A third? How wide is each of those pieces? A half? So each of those pieces is exactly what?
1/6.
Yeah, and how many are there? 1, 2, 3, 4, 5. So it appears the answer, once I find a common denominator, is 5 and 5/6. That was kind of tricky. We're going to have to do this again. So that was with mixed numbers. Remember I warned working with mixed numbers can be dangerous with calculations, and we're doing a calculation. So what's the alternative to mixed numbers? Improper fractions. Okay, so now we're going to look at it from an improper fraction point of view. So let's see, what was it? 2 1/3 times 2 1/2. So before we change this into improper fractions, redraw the grid we had, but not the inside, just the edge. So come down, make your ruler 1, 2, 3, and identify where 2 1/3 is. Draw the other way. Find your 1, your 2, your 3. Mark off your halves. Identify that right there must be 2 1/2. So the problem we found the first time we did it was that we had different denominators floating around and things were weird. So what was our solution with addition, with cutting cakes?
Make them the same.
Cut each cake like the other, yeah. I have to cut everything in half vertically and everything in thirds horizontally. Then it will start to make more sense. So I'm going to redraw my grid first with whole numbers. So my answer sits inside a 3 by 3 grid. And then I'm going to go through and cut my halves and thirds. So here's half, half, half. Go the other way. Thirds, 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 and so on. Now, having done this, we should be able to identify our. We should be able to identify our answer pretty quick. So here's 2 1/2, right? And here's 2 1/3 that way. So my answer is this box. So does the ruler at the top tell me how many halves I have? Yeah, how many, Minerva? How many halves to get to here? 3. Oh, careful. Hang in. 1, 2, 3, 4, 5 halves, right? So 2 1/2, I should write as 5 halves. And then counting down the other way to get to 2 1/3, 1, 2, 3, 4, 5, 6, 7. I skip one. 6, 7. No, that's right. This is equal to 7/3. So now I've redrawn the problem to show 7/3 times 5 halves. Okay. Let's see. How many little rectangles does my rectangle have in it? Well, we know this answer right away. How many lines across the top? How many spaces across the top here? 5 by 7. 5 by 7 is. So I know that my answer has 35 pieces. Next question, what does one piece mean? So here's a hole. How many pieces are in a hole?
6.
So now I have 35 out of 6. Way easier. So I go tell my mom I have 35 6 pieces of cake. Will she look at me funny?
Yes. Yes.
Yeah, she's not going to like that answer. She's going to like 5 and 5 6 better. Can't please everybody. So at first, mixed numbers are a pain in the butt to calculate with. Improper fractions are much easier to calculate with, and it doesn't matter whether you're adding, subtracting, multiplying, or dividing. Improper fractions are always easier than mixed numbers. But then I get an answer that I have to convert. Well, what makes a whole here? How many pieces? Couldn't I just go around counting groups of 6? Which is division, isn't it? Take 6 into 35, so we get to review division now. So just double check. Well, there's one group of 6. There's another group of 6. There's another group of 6. Another group of 6. 1, 2, 3. Here's another group of 6 over here. And then I have 1, 2, oh, not quite a group of 6 at the bottom. So what is that grouping tell me the answer must be also? How many holes were there? How many groups of 6?
5.
Yeah, 1, 2, 3, 4, 5 groups of 6. And how many left over? 5 out of 6. So I can still use the picture to go back and figure out what the mixed number version is. So that's the area model with numbers bigger than 1. A little bit more work with a bigger number, so there's going to be more. Let's compare that to algorithms. What's the difference between a model and an algorithm?
An algorithm doesn't show you how to get there, you just do the.
Doesn't show you why, it just shows you how.
Yeah.
Yeah. So it doesn't explain anything about why the answer should. This explains why the answer has to be 5 and 5, 6. Has to be that, or 35, 6, depending on your point of view. Right? An algorithm just gives me an answer. So we do have a multiplication algorithm. And it's just to multiply the numerators and multiply the denominators. Okay, so let's see, what was my original problem? My original problem was 2 1/3 times 2 1/2. Can I apply this algorithm to this problem directly? Adrian says no. The problem is I don't have 2 single fractions. I have fractions and this other stuff. So Adrian, can you do me a favor? Can you read me that number right there? 2 1/3. And literally the and means plus. That's 2 plus 1/3. This is 2 plus 1/2, 2 and 1/2. Order of operation wise, these guys are a unit and those guys are a unit. So that's what we really mean when we say 2 1/2 times 2 1/3. And that makes me think of algebra class. Now your kids are going to be doing this before they see algebra, but that's basically something like x plus 2 times x plus 3. What do you have to do to multiply that out? You start distributing, right? Do we really want to start teaching distributing at this point? Fractions are bad enough, right? I mean, they're not bad. They're beautiful. They're wonderful. But that adds a whole new level of pain and suffering, and we're just not going to do that. So this is, again, we want to change it to improper fractions. Right? So we use our little routine for that. 2 1/3 times 2 1/2. And so we have a little cyclical pattern here. 2 times 3 is 6. Plus 1 gives me 7/3. 2 times 2 is 4. Plus 1 gives me 5/2. And now I'm trying to do my algorithm. Multiply 35, multiply 6, convert back if you wish. Question: is that reduced?
Improper.
It's improper, yes. Is it reduced though?
Yeah, I think that's.
Yeah.
Yeah, there's no common factors. 6 is 2 times 3, and neither 2 nor 3 go into 35. 35 is 5 times 7, neither 5 nor 7 go into 6. So if we want a reduced answer, this sucker is reduced. It's a fine answer. Do I have to convert it back? It depends. If I just need an answer, that's fine. I love it. I'm done. If I need to use this in another calculation, that's the perfect number for the calculation. It's improper. But if I wanted to tell my mother about it, or like if Minerva wanted to know how far to drive to get more math help, right? I wouldn't say 35, 6. I would say 6 goes to 35 5 times with 5 left over. You know, go 5 and 5, 6 miles down the road, right? And that will get us there. So this is an alternate. It's not necessarily better than that. It just depends. This answer right here is more popular in conversation. Popular for conversation. We grew up hearing numbers like this more than we hear those when we're speaking to each other. things evolved differently, some different guy was in charge, maybe these would be more popular. It's just like Facebook happens to be popular right now. This happens to be the popular way to say fractions. Facebook versus MySpace? Yeah, maybe kind of, yeah. One of them's more expressive than the other one's kind of plain.
Have we ever said 35.6 though?
So that's a good question. Something that comes to mind that's related to this, pi is a crazy number. It goes on forever and doesn't repeat, right? So, you know, it's about 3.141 something something. For a long time, people realized that, wait a minute, something weird's going on with these decimals. We don't quite get it. And for thousands of years, we struggled with that. And a popular version of pi was 22/7. Now, I could write that. Let's see, 7 goes into 21 how many times? 3 with 1 left over. So I could call it 3 1/7. But it used to be a long time ago, fractions like that were more popular than mixed numbers. Way long time ago. It's just a matter of kind of like social convention with the people that are talking about this stuff. This guy's nice because I can find it on a number line easier. I can find 3 and move over a little bit. Right here, I have to count sevenths to get there. It's a little more work. They both have their pros and their cons. Just kind of depends. By the way, is pi exactly, anyone on your calculator, what's 1/7?
0.14.
Keep them. It's got more, right?
Oh yeah, 0.14285714.
5, 7. Oh, 1, 4. Oh, that's interesting. 1, 4, 1, 4. Might we guess what comes next? 2, and then 8, and then 5, 7. 1, 4, 2, 8, 5, 7. 1, 4. It's like a little train. 1, 4, 2, 8, 5, 7. 1, 4, 2, 8, 5, 7. Pi, on the other hand, goes 1, 5, 9, and then it goes blah, 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 forever and ever, but it never repeats a stamp. Like, I could make a rubber stamp out of this picture, and I could just walk down the street going stamp, 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 forever, and I would be trying to show this guy here as a decimal. It's impossible to do that with pi. You can't make a rubber stamp and make pi out of it. There's no stamp to ever make that happen, which is kind of weird decimal-wise. Oh, you're making me nervous. Oh, you have to go make a party, right?
I'm like,
Sure,
Are you
pack
on
your
this?
stuff on.
Those quizzes that you have?
That was just for fun to see
I was
if we're
trying
all
to
on the
make
same
that
page, communicating properly.
What about our person?
Oh, your person, you got to turn in, yes. Your mini, I definitely want that. Okay, so let's see, where was I? I got a little distracted by the popular convention here.
Sorry.
Let's see. Is there any, those are the main things I wanted to go over with stuff we've done. Do you guys have any things you want to go over based on the homework, projects, practice test? You're an easy crowd. So you have a take-home test. There's a practice test on the website.
Is there on the website that has your calculated answers?
Oh, that's a good question. Do I have answers online?
Is that
Would you like to see the answers? Yeah, I
Is
can.
this the test, or are we gonna have another one on Wednesday?
Yeah, so this is part of the test.
And there's gonna
This
be
is like
another
half of it, and there's going to be an in-class part on Wednesday.
Gotcha.
Yeah. I generally do tests in 2 parts, take home and in class. Doc.
I'll should look at Dr. Ryan's simulation.
Okay, so there's sample exam 1. Control F answers. Answers for exam 2. Okay, I will get answers for exam 1 there today.
So exam 1 sample will help us with the in-class one.
Yeah, it's going to be much like it. Sample answers. Okay, I'll get up there up right after class. Anything else you guys want to do?
Can you show me activity 9?
Activity 9, so is that division?
Yes.
Yeah, let's do a division problem together, okay? Let me bring that up. This is chapter 6, right? Okay, so down and almost. That's this one right here, right?
Yes.
Okay. Yeah, so this one, so here we're viewing division as finding groups in another one. So let's do one of these. Yeah. I'm going to jump to one on the next page. So on the second page, we're using just common blocks. Okay, so we'll do 5, 6 divided by 1/3 and see what happens. Five over 6 divided by 1/3. And we're using pattern blocks to model this. You could use Ks too. And then, let's see, division means groups in. So before I can draw this out, I have to state the question I'm trying to answer. And so the question this asks is how many groups of 1/3 are in 5, 6? How many groups of 1/3 are in 5, 6? And when you ask the question that way, it leads you to kind of draw the division box. So I'm going to try to preview this, wish me luck. So here's my division box. 1/3 goes on the outside because that's what I'm trying to push into the other one. So I have to draw my hole so I can find 1/3. And let's see if I remember right. We use the rhombuses to get 1/3. Does that sound right?
Yes.
Okay. So let me draw my rhombuses. Think like that. Okay, so 1/3 would be that guy right there, right? Okay, so then I have to draw 5, 6. Okay, so here's my hole. And let's see. Rhombuses again, cut this into 6. Okay. Drawing that right in. Again, did not go well. Now that. There we go. So there's my 6 pieces. I'm going to draw those with a slightly different color. 1, 2, 3, 4, 5. Okay, so now we're trying to find the 1/3 in the 5, 6. So we have to draw each like that. So division is a comparison. I do have to draw both. A little different than multiplication drawing. So let's see. I'm looking for this guy right here, right? And if I go over to this side, well, there's 1, right? And then here is another. And then I've got that. So how many groups of 1/3 did I find? Well, I found 2 and that. How do I describe that given what I'm looking for? It's half of what I'm looking for, isn't it? It's just 1 out of the 2 rhombuses I need. Yeah, so it appears there are 2.5 thirds in 5, 6. 1, 2.5 there. You see how I'm getting at, whatever? So So we got to count them. Here's the other way to look at it I went over in class last week. I'm looking for 2 blue rhombuses. And so how many groups of 2 live in the other side? Well, there's one group of 2, there's a second group of 2, and then there's one out of a group of 2 there. Yeah, so sometimes counting groups can help. Should we try another one? How about let's do 2/3 divided by 1/2 in 3. And then time. So 2/3 divided by 1/2. So first, what's the question that's being asked here?
How many groups of 1/2 are in 2/3?
Correct. How many groups of 1/2 are in 1/3? So we ought to write that down to keep us straight. How many groups of 1/2 that feedback? Ouch. All right. So that sets us up to do our kind of division thing. So I have to draw my 1/2 on the outside. And this is where that isometric dot paper comes in very handy. Some days I'm not good at drawing these. And so here is my 1/2. I think about my hexagons. All right, so next I have to draw my 2/3. And let's see, thirds makes me think of the blue rhombuses. So let's see, here is 1/3. And this guy right here makes 2/3. All right, so these pieces are pretty different shapes, right? So I gotta kind of break it down. I guess it kind of makes sense now to redraw my 1/2 in terms of rhombuses to match that one. So I'll redraw this guy. So I got to find some kind of common denominator to get me through this. And what am I looking for? Well, I would say I'm looking for a group of 3 rhombuses. Okay. Do I have any groups of 3 rhombuses on the other side? I got one of them, right? Color. So there's 1, and then I have this left over. So I have 1 and, how to describe that guy? 1/3, because it's 1 out of the 3 pieces I'm looking for. Yeah, so it appears that I have 1 and 1/3 of the pieces I'm looking for. So 1/2 goes into 2/3, 1 and 1/3 times. So I got to keep track of what I'm looking for. Groups of 3. How many groups of 3 are there? 1 and a little extra. You set that down, got that little extra. Here's one other way to look at it. I'm looking for 3 here, right? I have how many over here? Pieces.
1.
Altogether.
Oh.
I have 4 pieces, right? And so it always, when you need something and you have things, the answer always ends up being what you have over what you need. So let's check that out. I have 4 rhombuses, I need 3 rhombuses. You see a relationship between that and the mixed number we got? That's another way to look at it. I have 2/3, I need 1/2. So tab over in terms of groups in. All right, so that's all our time for today. If you guys have any questions on activities or homework over the next day or so, email me and I'll get back to you. Otherwise, take a look at that practice test that's online and you have the take-home test to work on. And I'm going to pause the recording.
How did,
Here. Hang on 1 sec. Actually, wait 1 sec. Mouse. Stop broadcast. I think you'll still be there if I do this, Debbie. Hang on.